Okay, so when we're talking about derivatives, slope, rates of change, we have two different lines. We have tangent lines, or we have secant lines. So secant lines are when you have a graph, 2 points, and you connect those 2 points. That would be the secant line. And this helps you find average rate of change. Because of course, if you want to find the average rate of change between 2 points, you would do y2 minus y1 over x2 minus x1. So that'll tell you what the average rate of change is over time. And of course, since that happens to be a linear function, that average rate of change would also be the always rate of change. But if you had a situation where you have 2 points or 3 points on a line, okay, or if we just think of a curve itself, if I were to take any 2 points on this curve, maybe I'll pick one like up here so you can see it a little better, and then I were to connect these two, this would create a straight line. Now the slope of that straight line wouldn't be identical to the function itself since it's a curve, but this would be the secant line between 2 points, and that would find the average rate of change over that period of time. A tangent line, however, is if we take any curve, we can create a tangent line on that curve, which is where we have a single point on the curve, and we draw a perfectly linear line that touches the curve exactly once. And the slope of this line, tangent line, this is what we get from taking the derivative of a function. So if you take the derivative of a function, say you have y equals x squared plus 4, and you were to take the derivative of that, that would be 2x. This goes away because it's a constant. Now, if you were to take this equation and you were to plug in some x value for it, so let's say we plug in when x equals 1, well, when x equals 1 here, 2 times 1 is just 2. So that means that if you were to look at the function when x is 1, the slope would be 2. So it gives you a formula that would find the slope at any point. So that's the background of it. Now, where this comes into the limit definition. So the limit definition of a derivative is this. And this just comes from essentially finding the slope. So if you were to have a graph and you have 1 point, any point, we're going to use variables, x, then its y value would be f of x, of course, because the y value is always f of whatever the x value is. And then if I were to have another point over here, so let's say the horizontal distance between these 2 points is h. We'll just represent it as h. Well, I know the x coordinate here would be x plus h. And then it would be f of x plus h, just because that's the horizontal distance, which is h. So if we were to calculate the slope with these 2 points, we would do y2 minus y1 over x2 minus x1. And then of course, you're going to see down here, these x's are going to cancel out, and then you're left with f of x plus h minus f of x over h. And this, of course, would, if you were thinking theoretically, that would find the secant line between these 2 points. That's what that would do in particular. Now, remember, if we're trying to talk about, since this is the definition of derivative, we know that derivative differs from the average rate of change, because average rate of change calculates an average over a certain amount of time. Derivative calculates instantaneous rate of change. So derivative is instantaneous rate of change, meaning it finds the rate of change at an exact value. So that's where it differs from average rate of change, and derivatives always model tangent lines because it's at that exact point. Now we have slope, or average rate of change, which models average, and it's represented by a secant line. So we need to find a way to take this formula and rewrite it in a way that it represents the derivative, instantaneous, as opposed to average. So that's where the limit part comes in. The limit as h approaches 0. And the reason we have to put this in to transform this from a regular slope or average rate of change problem into calculating derivative is because the derivative at any given point is always going to be what the function is doing at that exact point. So if we think about this, as h approaches 0, so what would happen as h approaches 0? If we think of limits, if you think back to what limits are, limits talk about what a function is doing basically as it approaches a value. So for example, if we were to look at this function, and let's say it has a hole at, 3, 2. The limit as this function approaches 3 is still 2, even though it actually doesn't take on that value. It's what it's doing as we get there. So that's why that's important to think about here. So if this distance is approaching 0, as we approach 0, this distance shrinks, and it shrinks, and it keeps shrinking, tiny, 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 until it becomes nothing. Now, of course, if the distance between these 2 points doesn't exist anymore, we're finding the instantaneous rate of change at a particular value. So that's where the definition comes in.